Hello everyone. In this lecture I shall discuss the polar form of a complex number for which we need the detailed understanding of the argument or amplitude of the complex number. Subsequently we will discuss the nth root of complex number as well as the nth root of unity. Now if you recall a complex number with its geometric representation, we have z is equal to x plus iy. In ordered pair form we write x comma y, where both x and y are the real number and I square is minus 1, or I is a point on the imaginary line, okay, on y axis. So geometrically we know a complex number is a point in the organ plane or complex plane, right, in the complex plane, while the real number is a point simply on the real line. Now coming to the geometrical representation, if you have your x-axis, horizontal axis, and your y-axis, the imaginary axis, right, imaginary axis. Now coming to the geometric representation, we have our real axis and we have x and imaginary axis y. Now let I consider a point. I consider a point xy point. This is a point xy, and this is my z. This is my complex variable z. So now this is my y. This is my y, and this is my x. This is my x. Okay. So this distance is my x here. So now if I join this diagonal here, right, if I join this diagonal here, then this diagonal on making an angle, you see this is a right angle, is not it? So now if I say this is my theta, the angle is theta, and definitely this is my origin here. Now this distance is my z mode, right? You know, this is the distance from origin to the complex number z. Let I denote it my r, right? Then it is easy to see from the geometry that you have here x is equal to r cos theta, right? If you put x is equal to r cos theta and y is equal to r sin theta, right, then the same thing will also hold. So therefore with this, what is your r? Your r is equal to z mode. The absolute value is your x square plus y square root over, as you know, sin square theta plus cos square theta is your 1, right? So definitely this will hold. Now this z mode is called what? This is my absolute value or modulus of z. Now what about your theta, right? Your y by x is tan theta. So what about your theta? Your theta will be tan inverse y by x, right? This theta will be tan inverse y by x, and this is called the argument or amplitude of your z, right? We write it argz or we write ampz, okay? So before the details of the discussion of the argument of z or amplitude of z, okay, let me to introduce myself, Professor Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the details about the argument, and subsequently we will discuss the polar form of the complex number. So in view of this, so what will happen to my complex number now? So this complex number now can be written as with this, right? With this you will able to write it you will able to write it. You see, you will able to write it. Here x is r cos theta and y is your r sin theta, right? So you can write it here. Z is equal to r cos theta plus ir sin theta. So that will be your r into cos theta plus I sin theta, and this will be your polar form, right? This will be your polar form of complex number, polar form, right, of complex number with your r is equal to modulus of z. It is the distance from origin to z, and theta is equal to your argument of z, tan inverse y by x, what we call the argument of z. Okay, so let us discuss the details of this. So now if this is my origin O, right, this is my origin O and this point is my P, then what is theta? Basically theta, the direction is positive direction. So basically theta is the directed angle, in the positive direction from the, or I write from the positive x-axis to OP, right, to OP, right? So now let us discuss the argument or amplitude of z in details. Suppose I have a complex number 1 plus I, z is equal to suppose 1 plus I. So this is my 1. What is my tan inverse y by x? Tan inverse y by x is the here tan inverse y by x. Tan inverse y by x is your theta, is your pi by 4. So how I can write it? So if this is my point P here, so this angle should be my pi by 4. This angle should be my pi by 4. Okay. So I can write it. Z is equal to, and what is your z mod? And your modulus of z is equal to root 2. So I can write it root 2 cos pi by 4 plus I sin pi by 4, right, I sin pi by 4. Now the question is, suppose I have a number -1 minus I. Okay, suppose I have a point z is my -1 minus I. Z is equal to -1 minus I. So now in view of this, right, what is my z mod? Z mod is equal to r is my root 2. And what is my theta? If theta is my tan inverse y by x, it is here 1, right? So can it be pi by 4? Now the question is, can this angle be pi by 4, right? Can this rotation be pi by 4? It cannot be, right? It cannot be. It should not be your pi by 4, but you see that here it seems to be pi by 4, right? Pi by 4, but you see, can this angle be pi by 4? But it cannot be. It is not pi by 4, right? It is not pi by 4, right? So for which we have to classify the argument, right? So just writing theta is equal to tan inverse y by x is not the solution. So we have to classify the argument. If it is in the first quadrant, then what is the argument? If it is in the first quadrant, then what is the argument? If it is in the second quadrant, then what is the argument? If it is in the third quadrant, then what is the argument? If it is in the fourth quadrant, then what is the argument? Okay, so we will classify the argument, right? We will classify the argument into two types. Argument of z can be classified into two types, right? Can be classified into two types. One is the general argument. And it is denoted by, and another one is the principal argument. The principal argument is what? This principal argument we denote it by This argument is basically denoted by A, R, G, Z. You see, this is small a. This A is small letter, okay? Small a, small letter. While here principal argument is, we write it capital A, R, G, Z. So it is here capital letter here, capital letter. Okay, so basically we will denote it. So what actually this principal argument means? So we have to classify it. What actually this principal argument means? It means the smallest angle created with x-axis, right? Smallest angle created with x-axis. So x-axis may be positive or negative direction, right? Maybe here positive or negative direction, positive or negative orientation, okay? And this argument has to be restricted within this limit. Minus pi is less than here argument of z, and which is less than is equal to here pi. So that means here principal argument of z, that is principal argument of z lies in open interval minus pi. It cannot be included, but close interval pi. So this principal argument has to lie in between this. This is most important. Okay, now this general argument can be viewed as you see, this argument of z here is here principal argument of z plus and minus 2n pi, right? As you know, sin theta is periodic with period 2 pi, cos theta is periodic with period 2 pi. So you see, this argument of z is argument of z plus minus 2n pi. So this general argument is not unique. So what we conclude, this argument of z is not unique, right? It is a multi-valued function. If theta is a argument, then theta plus 2 pi is a argument. Means here theta, if theta is a argument, theta is equal to also your theta plus 2 pi, right? 2n pi, right? We can, in view of this, we can write. That means my argument of z is, so here I can write n belongs to the natural number, right? N belongs to n star, natural number including 0. Now I may also write my argument of z is argument of z plus 2n pi. If I omit this minus sign, then I must write n belongs to z, okay? Because in z plus minus 1 plus minus 2, okay, everything is plus terms and minus terms are there. So now this is the relation between the principal argument and the general argument. So in view of this is not unique. So I can write it my theta is equal to my ARGZ, which is same thing as theta plus 2n pi, okay? N in z, right? N in z. So argument of z is not unique. If 2 pi is argument, 4 pi is argument, 6 pi is also argument, like that, because sine and cosine are the periodic function with period 2 pi. So now we have to understand the principal argument of z. We have to understand the details of the principal argument of z. Now, as you know, the principal argument, it is denoted by capital A. It has to lie within this. So now to view this principal argument, we have consider the complex number in any quadrants, okay? In any quadrants. So it is my plus, it is minus, and it is my minus, it is my plus minus. So it may be in any quadrant. So now if I take my, suppose some alpha is equal to, suppose I take tan inverse y by x modulus, ignoring the negative sign, right? Ignoring the negative sign. Then if it is in the first quadrant, here, if it is my z is here x plus iy, then my this angle is my alpha. This angle is my alpha, is not it? So alpha is same thing as theta, is same thing as tan inverse of y by x, which is same thing as tan inverse of y by x modulus, because there is no negative sign. So in the first quadrant, right, I get the principal argument here. So my capital ARGZ here, which is my capital R ARGZ, capital ARGZ here in the first quadrant. Now if it is in the second quadrant, then what will happen to the principal argument? If it is in the second quadrant, you say, suppose my Z is here, Z is equal to my minus X plus IY, Z is here. Now this is actually the rotation in positive orientation, however this angle is the smallest one, is not it? However this angle is the smallest angle, is not it? Is it not your negative x-axis here? So right, so however this is my smallest angle. So what is the smallest angle? This complete rotation is 2 pi, so I can write here ARGZ is my, this complete rotation up to this complete rotation is my pi, so it is pi and minus, if I say this is my alpha, I can write it pi minus alpha. Okay, so it is my pi minus alpha, right? Now if it is in the fourth quadrant, then what will be my principal argument? If it is in the third quadrant, what is my Z? Z is suppose minus X minus IY. Okay, suppose this is my Z. So in the third quadrant, what will happen? So if I say suppose this is my alpha, right? Now is it not the smallest angle? Is it not the angle created with x-axis? So what is my argument of Z here? Now this total is my say alpha, so it is my alpha minus pi, up to this it is pi, so it is alpha minus pi. So in the third quadrant the argument is alpha minus pi. Now coming to the fourth quadrant, what is the argument? In fourth quadrant your argument will be, the argument will be, suppose I am here, so Z is equal to X minus IY. So then this here, so is it not the smallest angle created with x-axis? Maybe negative direction, no issue. So now if this is alpha, then your argument of Z is simply my minus of alpha, right? Minus of tan inverse y by x mod, right? This is my simply minus of alpha. So here this argument of Z is this. So accordingly we can write the argument, right? Coming to one example, suppose you are given Z, right? 1 plus I minus 1 plus I minus 1 minus I and 1 minus I, and if you think here and here, this is your 1 plus I and this is your minus 1 plus I and this is your minus 1 minus I and this is your 1 minus I, right? So now it is in the first quadrant, so let my alpha is equal to tan inverse y by x mod, right? So maybe 1 or minus 1, whatever it may be. So it is here simply tan inverse 1 is pi by 4. Okay, so therefore I write argument of 1 plus I. So it is in the first quadrant, it is simply tan inverse of y by x mod is here pi by 4. Now if it is in the second quadrant, then what is your argument of 1 minus 1 plus I? It is in the second quadrant, so it is my pi minus tan inverse y by x mod, right? So this is pi minus pi by 4 is 3 pi by 4. So this will be my 3 pi by 4, right? So I will take this is the 3 pi by 4 here. So this is my pi by 4 here and this is my 3 pi by 4 here. And now if it is in the third quadrant, then my argument of minus 1 minus I, then it will be here tan inverse y by x mod minus pi. So this is my pi by 4 minus pi. So it is my minus 3 pi by 4, So it can be viewed as minus 3 pi by 4 here, right? It can be viewed as minus 3 pi by 4 here, right? Then what is my argument of 1 minus I? It is in the fourth quadrant, it is simply minus of tan inverse of y by x mod is minus of tan inverse of 1 is minus pi by 4. So is it not the smallest angle? So here the smallest angle is here, so this will be here minus pi by 4, right? This will be your pi by 4, this will be your minus 3 pi by 4, and this will be your 3 pi by 4. So in that way we can understand, in all the cases you see this, all these cases here, this argument has to lies in between here pi, minus pi to pi, plus pi is included, minus pi is not included. Okay, so this is what your principal argument. So once we find the principal argument, then you will able to get the general argument. If I ask what is the argument of 1 plus I, so you can write pi by 4 is an argument, pi by 4 plus 2 pi is an argument, pi by 4 plus 4 pi is an argument, pi by 4 minus 2 pi is an argument, and so on. So you see this argument d4 by 2 pi. You see, if you think of this difference, right, this is d4 by 2 pi, d4 by 2 pi, and anything you see it is d4 by 2 pi, this gap is d4, right? So this argument, the general argument may differ by 2 pi. Thus we can say here argument of z small arg, argument of z is a multi-valued function, right? Because we are getting different value for the same z. However, the functional value differ by multiples of 2 pi, okay, right? So while we compare these properties, the property may vary. We have to see that they differ by 2 pi, then also it is okay. You see this gap is 2 pi, right? But if I think this and this gap, what is this gap? The gap is 4 pi, so it differ the multiple of 2 pi, right? However, this principal argument of z is a single valued function, right? And as such, it is the functional value is argz less than equal to pi. So it lies in between minus pi and pi. So you see, though here fz is equal to argument of z is a multi-valued function, but here fz is argument of z is also a single valued function, can be a single valued if z in k plus 2 pi, right? If we restrict the interval, then it can be also converted to single valued. And also, as you know, argz plus 2n pi is here argz, general argument and principal argument, right? If you restrict the interval, then it can be also converted to a single valued, but as usual, principal argument is single valued, but general argument is multi-valued. You know, every real number is a complex number. So now if here z, if z is equal in here r plus, or z in here r minus, right? Then what will happen to your argument of z? So you see, in r plus means here z is here in r plus, then what is the argument here? The argument is here 0. Right? If z in here r minus, then what is your principal argument? Argument of z. If z is here, right? If z is here, anything here, then the argument of z is here pi, right? Argument of z is here pi. Now what happens to your IR, IZ, argument of IZ here in this case? What will happen here? In this case, your argument of IZ, it will be here, it will come over here, right? It will be here somewhere, what? So here it is pi by 2, and here the argument is 0, here the argument is pi, and here the argument is minus pi by 2. Then the argument of IZ here for z in r plus is here pi by 2, and here in this case the argument of IZ here will be here minus pi by 2, right? So therefore if I write what is argument of 5 is argument of half is equal to here argument of 100, because all are belongs to your z r plus. So here it is 0. If I write argument of minus 10 is your argument of 25 minus 25, or argument of minus 0.5, whatever I write. So here it is in negative real axis. Okay, it is your pi, right? Similarly, if I write argument of I, argument of 5 pi, whatever it may be, it will be your pi by 2. And if I write argument of minus I, argument of minus 10i, whatever it may be, argument of minus I by 2, these are all in the negative imaginary axis. Okay, so this will be minus pi by 2. However, what will happen to the argument of 0? Argument of 0 is undefined, right? Argument of 0 here, you note that argument of 0 is undefined, Why undefined? Because tan inverse y by x, right? Tan inverse of y by x, it is not valid if x is equal to 0, is not it? So this argument of 0 is undefined. However, modulus of 0 is what? Z is equal to 0. What is the modulus of z? Modulus of z is equal to 0 is 0. The modulus is valid, but the argument is not valid, right? So you should note that this is important. Argument of 0 is undefined. Now coming to properties of the argument. So now if you discuss the properties of the argument, as you know, your ARGZ is equal to, your ARGZ is capital ARGZ plus 2n pi. Okay, n in z here is the set of integer, or I can write n in your integer, set of integer. Okay, n in I, right? You know this. So now the properties of the argument we will see. The properties of the argument we will see. Argument of z1 into z2 is argument z1 plus argument z2, right? If we want to prove it, suppose I want to prove it means z1 is equal to r1 cos theta plus I sin theta 1, it is theta 1, and z2 is equal to r2 cos theta 2 plus I sin theta 2. Now if I multiply it r1 into r2, okay, so then it will be r1 r2 cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So what we are getting here? So the argument here is theta 1 plus theta 2, right? So therefore it is z1 into z2. So therefore what we conclude? Here argument of z1 z2 is here theta 1 plus theta 2. So this is equal to argument of theta 1 plus argument of theta 2. And since it is a multivalued function, and here we can see the LHS and RHS may vary. LHS and RHS may vary, right? With a difference of multiple of 2 pi, multiple of 2n pi. Okay, right? The left hand side and right hand side may not be exactly equal, but you can see may vary this. Now if likewise if I think of suppose here argument of z1 z2 so on up to zn, then what does it mean? Here argument of z1 plus argument of z2 plus argument of zn. If we want to see this geometrically, now suppose this is my real axis and this is my z1, then this argument here will be theta 1. Suppose this is my z2, then this argument will be my theta 2, right? And suppose it is my zn, then this argument here will be here, theta n, right? Now here this is z1 into z2 into z3 up to zn, and this argument and this will be the sum of, right, theta 1 plus theta 2 plus, or I can write the summation of theta I. I can write it as the summation of theta I. It is summation of theta I is equal to 1 to n. So in that way the product of complex numbers can be viewed geometrically, which is not possible in the vector sense to see the product of the vectors. Okay, even the geometric representation of complex number is resemblance to vector, but in vector we fail to find this, right? Fail to represent this product of n vectors diagrammatically. However, if you see, for in view of principal argument, in view of principal argument, we see ARGZ, we see in view of the principal argument this, we see argument of Z1 Z2 not equal to, in general, argument of Z1 plus argument of Z2. However, it will equal under certain restriction. However, argument of Z1 plus Z2, Z1 into Z2 is argument of Z1 plus argument of Z2 if and only if this lie in the interval ARG-Z1 plus ARG-Z2 lies in the interval this. Okay, this is the restriction of the principal argument. So likewise, all the property will be extended in that way. So likewise, argument of Z1 by Z2 is not equal to 0 is difference of this, provided this lies in the given range. Okay, this is the restriction for principal argument. And similarly, this 2 here, argument of 1 by Z is minus argument of Z if and only if Z not in this, Z not in negative real axis, right? Then only this will hold and this will hold, but this restriction is not there for principal argument. Okay, now let us solve an example. Suppose you are given Z1 is equal to minus 2 plus 2i and Z2 is equal to 3i, right? You have to check this argument. So what will happen here? Here Z1 into Z2, if you multiply this 2, it will be minus 6i. Z1 by Z2, it will be 2 by 3 plus 2 by 3i, 2 by 3 plus 2 by 3i, and you are asked to find ARG Z1 into Z2 and ARG Z1 by Z2, and you verify. Okay, so here what is the argument of this and what is the argument of this? The argument of Z1, so what is the argument here? This is lies in the third quadrant. So argument of Z1 Z2 is equal to, it is tan inverse of minus 6 by 6, 1 minus tan inverse of minus 6 by 6 minus here pi. So this is equal to pi by 4 minus pi is here minus 3 pi by 4, right? And similarly here argument of Z1 by Z2 is here pi by 4, it lies in the first quadrant. But what happens to the argument of this? Here argument of Z1 simply, it is in the second quadrant. Okay, second quadrant. So it is pi minus pi by 4 is here 3 pi by 4, and here argument of Z2, it is in the imaginary axis, is pi by 2. So what will happen here? Here argument of Z1 Z2, right, is here minus 3 pi by 4, but argument of Z1 plus argument of Z2 is here 3 pi by 4 plus pi by 2 is here 5 pi by 4. You see, this is not equal to this, right? This is not equal to this. However, but 5 pi by 4 minus 2 pi is minus 3 pi by 4. Okay, so this is this and this not equal, right? However, this is this, so it differ by 2 pi here, and this restriction here is lies in between this interval minus pi to pi, as the principal argument requires to lie. Now coming to the nth root of a complex number, let here z is equal to r cos theta plus I sin theta. Okay, so what is your z to the power nth, z to the power nth root of z? Now what is z to the power n? Your z to the power n is r to the power n cos n theta plus I sin n theta. You know this because this is de Moivre's theorem. De Moivre's theorem. You know this. Now from this viewpoint, if you are asked to find the nth root of z, okay, if you are asked to find the nth root of z, so this is equal to r cos theta plus I sin theta whole to the power 1 by n, is not it? So you will able to write it. It is r to the power 1 by n, and you can split in view of the general argument. It is cos theta plus 2k pi plus I sin theta plus 2k pi, right? Because 2k pi is the period, this to the power 1 by n. Now here z to the power n is this to the power z to the power n is what? Z to the power n is this to the power n into this to the power n. Z is simply r cos theta plus I sin theta. So z to the power n is this. So now this n is multiplied here. Okay, so similarly, so this will be multiplied here. So this will be here r to the power 1 by n cos theta plus 2k pi divided by n plus I sin theta plus 2k pi divided by here n. Okay, so with here k varies from 0 1 up to n minus 1. So here nth root of z involves how many roots? N roots. So we are getting how many this is n roots, is not it? 0 to here n minus 1, n roots. In that way we'll find the nth root of the complex number. So if you think it geometrically, this all the n roots, okay, all the n roots we are getting z0, z1 up to zn. These n roots of the complex number lie on a circle of radius r to the power 1 by n. So it will lie on a circle of radius r to the power 1 by n, and these are the polygons we have to take. Okay, so these are the points, these are the vertices of the polygon. Okay, these are the vertices of the polygon. So it lie on the circle, the radius of the circle, right? This is the radius of the circle is r to the power 1 by n, and this is z0, z1, z2, z3, likewise here zn minus 1. Okay, so this is the geometry. Now if we think of this restrict to 1, nth root of the unity, right? If you extend it to nth root of unity, here z is equal to 1, here is 1, so here 1 you can write it cos pi by 4, cos pi by 2 plus I sin pi by 2, cos pi by 2 plus I sin pi by 2, because 1 is here, so your argument of z is equal to here 0, if your z is equal to 1 means 1 will lie here. Okay, 1 is here. So what is the argument? Theta is equal to 0 here. It is 0, I 0. And what is z mod? Z mod is equal to 1. So now you add, it is cos 0 plus 2k pi plus I sin 2k pi. Okay, so now what is z to the power 1 by n? Z to the power 1 by n is cos 2k pi by n plus I sin 2k pi by n. In that way we will find. So here k is equal to 0, 1 up to n minus 1. In particular, if I find the nth cube root of unity, suppose I find cube root of unity means here zq is equal to 1. This is cos 0 plus I sin 0. So this is equal to cos 2k pi plus I sin 2k pi. So what is your z? Z is your cos 2k pi by 3 plus I sin 2k pi by 3. Okay, so here k is equal to 0, 1, 2. If I put k is equal to 0, then what is my z? My z is equal to cos 0 plus I sin 0 is 1. If I put k equal to 1, I find here z is equal to minus half plus half 1 by 2 root 3 I. Okay, and I call it omega. And for k is equal to 2, I find k is equal to 2, I find z is equal to minus half minus 1 by 2 root 3 I. Okay, so here we can say this is your omega, this is your omega, and this is your omega square. If we find the square, then this cube root of unity 1 plus omega square is equal to 0, but omega q is equal to here 1, and this will lie here in a circle of radius 1. Okay, and here it is a triangle. If this is a circle of radius 1, it will form a triangle with this 1 is a vertex, this 1 is a vertex, and omega is a vertex here, and omega square is a vertex here. So it is a polygon, as you see, it is 3. So likewise, if here cube root of 4, okay, if you find cube root of 4, so here likewise we can say the nth root of unity lies on a circle of radius 1 and center at origin and constitute a vertices of regular polygon. So as you see, the cube root of unity, okay, so we have 3 vertices on the circle of radius 1 and center at origin, right? And similarly, if I think of here z to the power 4, z to the power 4 is equal to 1. So this is equal to cos 2k pi plus I sin 2k pi. So this zq is equal to 1. You can write it like this. So here k is equal to, if you solve it, k is equal to 0, 1, 2, 3. We will find 4 points here. So these are the vertices of this regular polygon. Okay. So likewise, some standard polar form. Suppose z is equal to 1, then you write it cos 0 plus I sin 0 means cos 2k pi plus I sin 2k pi. Likewise, if you have here z is equal to minus 1, then it is cos pi plus I sin pi, and accordingly you can extend. Suppose your z is equal to I, it is cos pi by 2 plus I sin pi by 2. Suppose your z is equal to minus I, it is cos pi by 2 minus I sin pi by 2, because the argument is minus pi by 2, here it is cos pi by 2 plus 2k pi. Similarly, plus minus I sin pi by 2 plus 2k pi. Okay, so suppose you are asked, solve z to the power 8 is equal to 1. So you will write it, it is cos 2k pi plus I sin 2k pi, or it is e to the power I 2k pi. Okay, so what is my z? So this implies my z is equal to cos 2k pi by 4 plus I sin 2k pi by 8 by 8, or I can write e to the power I k pi by 4. Okay, here k is equal to 0, 1, 2 up to 7, 8 roots. For k is equal to 0, here z is equal to cos 0 plus I sin 0 is equal to 1. Okay, z, suppose I say z1, and for k is equal to 1, I have my z2. z2 will be cos pi by 4 plus I sin pi by 4. Accordingly, it is my 1 plus I by root 2. Okay, similarly, I have k is equal to 2, z3 will be, so it is for k is equal to 2 you are getting, z3 is cos pi by 2 plus I sin pi by 2. So sin pi by 2, this is 0, sin pi by 2 is 1, and for 3 it is 3 pi by 4 plus I sin 3 pi by 4. So it will cos 3 pi by 4 is minus half, it is minus 1 plus I by root 2, and sequentially here z5 will be the negative of z1, sequentially it is the negative of this, then z6 will be the negative of z2, and z7 will be the negative of z3, and z8 will be the negative of z4. So this is equal to here minus 1, this is minus 1 minus I by root 2, this is minus I, and this is 1 minus I by root 3. So these are the 8 values. If we do not know the value, we will just leave it in this form, e to the power I pi by 4 and I will write it simply e to the power I pi by 2. I write in this way. In this way I will write e to the power I 3 pi by 4. Right? In that way we can write it. We can leave it. If we do not know the value, then we may leave it of this form. Okay. Find the square root. Suppose you are given z is equal to x plus or minus I y. So this is my sine of y. Okay, or I can write it x plus I plus or minus y I can write. So this is my sine of y. Right, sine of y. So what is the square root of z? Here what is r? R is equal to x square plus y square root over. And what is the square root of z? It is plus and minus r plus x by 2 root over plus I, and I write the sine of y, right, into r minus x by 2 root over, right, r minus x by 2 root over. For example, suppose you are asked to find the 3 plus 4i root over. So what is r? 3 square plus 4 square root over is 5. So what is this root over here? It is plus and minus 5 plus 3 by 2 root over, and plus, this plus is here, so I write plus I 5 minus 3 by 2 root over. And what we can write here for this, what is my r? R is 5 here, so this root over is my plus and minus 5 plus 3 by 2 root over. It is minus, so I write minus I, it is 5 minus 3 by 2 root over. So what is the value then? It is 5 plus 3, 8 by 2 root over 4, 2. So this, so I can write is 2 minus I and minus 2 plus I. And here what I can root? 2 plus I and minus 2 minus I. So these are the roots. Okay. Coming to example 1. Suppose you are asked, find ARGZ and ARGZ. Principal value and general value. So here it lies in third quadrant. It lies in minus 5. It is in second quadrant. So what is my alpha? Alpha is tan inverse of, this is minus pi by minus pi is here tan inverse of 1. Is tan inverse of 1 is here pi by 4. And so here in third quadrant, what is here ARGZ? ARGZ is here alpha minus pi. It is pi by 4 minus pi is minus 3 pi by 4, is not it? And what is here ARGZ? Here ARGZ is ARGZ plus 2n pi. N is an integer. Accordingly, in the second quadrant, what is here ARGZ? ARGZ is pi minus tan inverse of y by x mod. It is pi minus pi by 4 is 3 pi by 4. So here ARGZ accordingly, here ARGZ plus 2n pi. N in z. Okay. Now write the polar form of this. So first you simplify it. What is your z now? So z is equal to, you multiply its conjugate in the numerator and denominator, 1 minus I square by, it is 1 plus I into 1 minus by a 2, 1 minus I into 1 plus I. So this is equal to 1 plus 1 minus a square plus b square. B square is minus 1 minus 2i by 2. So this is equal to minus I. So if it is minus I, so then argument of z will be minus pi by 2. What is your r? And what is your z mod? Z mod is minus I mod is equal to 1. So what is your r? So therefore your z is equal to r cos theta plus I sin theta. So r is 1. It is cos pi by 2 minus I sin pi by 2. In that way we will write. Suppose you are asked, solve this. It is ax square plus bx plus c. So z is equal to minus b plus minus root over of b square minus 4ac by 2a. So that formula I have applied. So now b is here this, right? C is here this. This is b, this is c. So accordingly you get it, the square root. I have told you the square root here. So if you simplify, you will get two roots. Z1 is this and Z2 is this. And coming to one more example, here it is fourth power. So you put z square is equal to put z square is equal to some p. We need 4 roots here, z1, z2, z3, z4. So how to solve it? So it is now my p square minus 3 plus 6i p minus 8 minus 6i plus this. So this is here ax square plus bx plus c. So here p is equal to minus b means 3 plus 6i plus minus root over of b square means 3 plus 6i whole square minus 4ac minus 4 into a is here 1 into c minus 8 plus 6i by 2. So now you can find the square root of the complex number. So you are getting p1 and p2 after that. So that means my z square is equal to p1 p2. So implies my z is equal to plus minus root over of p1 and plus minus root over of p2. So here we are getting 2 roots here, say z1 z2, here z3 z4. In that way you will able to get it. Okay, the video is getting lengthy, we should conclude here. To conclude you are coming to the complex number. It is important to write it in polar form for further analysis, for write the nth power, and for complicated cases we need to bring it to polar form. So for which we need the argument, right? Argument are of two types, principal and general. So we cannot directly find the general argument, we have to find the principal argument, then that restriction should be confirmed. Okay, and then we'll find by adding 2 and pi we will get the general argument, right? Accordingly you should solve some problems from any standard books. Now if you feel, though the video is lengthy, too many things are there, so if you feel this lecture is interesting and helpful, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures. And by once it is uploaded, if you subscribe to this channel, it will be come to your screen, okay, which will easy to access for you. So let us close this lecture here. Thank you all. And my upcoming lecture will be complex valued function. It is most important, complex valued function, right? Then limit, differentiation and integration, subsequently we will extend it. Okay, so at this stage we should conclude the lecture. Thank you all, have a nice day.